when we calculated the magnetic field of a long wire, let's now consider this wire to be an infinite wire, and looking at the limit where the length goes to infinity, we discovered that at a point P here, that if our current was running like this, our magnetic field was pointing in the direction out of the plane of the figure. And if we drew our field line, so let's just draw our field line like this, then here it's into the plane of the figure for our B field down here, coming into the plane of the figure, and our field lines were like that. And if we chose a coordinate system where we picked say a right-handed system, so we have r hat, we have theta hat, and r hat cross theta hat is our k hat direction, the direction of the current, then we could write our magnetic field up here at the point. Doesn't matter where we are because of our polar coordinates. It was given by mu naught times I divided by 2 pi. Now let's call this distance r. It's 2 pi r theta hat. And this came from the Biot-Savart law. Now, we like to make this the starting point for another one of our fundamental equations of magnetostatics, which is called Ampere's law. Now, the way we'll do it is we're going to consider first the case of just an infinite wire, and we'll have the infinite wire that is going into the plane of the figure, out of the plane of the figure, here I. And let's choose a path that's a circular path. So this is a circular path. And recall that our field, our B field, will point tangential. And along this path, we're going to make it a radius r. And what we'd now like to calculate is the line integral of B around that closed path. So let's do the line integral of B around the closed path. And what we want to do is take this line integral, so by the right-hand rule, our thumb is pointing in the direction of the current, and we're circulating around this line integral in a consistent direction. So what is this integral equal to? Well, we can write ds as a small arc length here. So we pick an arc length of angle d theta and radius r. So we have r d theta theta hat. And this is where we use our Biot-Savart law to calculate the magnetic field. And theta dot theta hat is, of course, 1 unit vector. So our integral becomes mu naught I over 2 pi r times r d theta going around the closed path, theta, let's take it from 0 to 2 pi. Well, you can see the r's cancel, and what we get out of here is mu naught I 2 pi, and when you integrate d theta from 0 to 2 pi, you get another 2 pi, and so we just get mu naught I. Now, this is a basic calculation for a very symmetric configuration where we have this infinite wire carrying a current I. But what we'd like to do is now set up how this law is actually quite general. And the statement of the law will be that the line integral of B dot around a closed path is equal to mu naught times what we call the current enclosed. Now, if I take an arbitrary path, and I can have, we'll end up calling these paths Amperian paths or Amperian loops. And if I have current, some going this way, I1, another pointing in the opposite direction, one here, I3, out here, I4, another one, I5, then in this line integral, the currents, depending on whether they're consistent by the right-hand rule with the way we're circulating around this path, that the ones that are consistent in the same direction, like I1 and I3 will have positive signs, I2, because it's going the other way, will have a negative sign. I4 and I5 are not enclosed. And what we want to show is that in this particular example, this integral will just be mu naught times I1 plus I3 minus I2.